So we define an acceleration as a change in velocity over a change in time, right? And a uniform acceleration is when this velocity is changing at a constant rate. So, for example, we might have an acceleration of 9.81 meters per second squared down. And what this means is that the velocity is changing by 9.8 meters per second every second, right? So at time 0, it might be changing at, the velocity might be 0. At time 1, it'll be 9.81. At 2, it'll be twice that much, etc. So that's true about how the velocity can change in terms of the magnitude. But what happens if the velocity changes in a different way? What if we keep the magnitude the same, but we change the direction? Does that still count as an acceleration? Well, let's think about it for a second. We define acceleration as a change in velocity over a change in time. Is a change in direction a change in velocity? And it is. So we can actually define a delta v as a change in direction as well. So what this means is that an object that's changing its direction, even if it's moving at a constant speed, will also be accelerating. And the most common example of this is circular motion. Circular motion is when stuff moves in circles. Pretty straightforward. Now, according to our definition of acceleration and velocity, this means that an object that's following a circular motion must be accelerating because its direction is constantly changing, right? For example, if you're in a car on a circular track, right? Over here, if you're driving this way, your velocity is going to be in this direction. Over here, it's going to be in this direction. Over here, it's going to be in this direction, etc., right? So even if you're driving at like 25 kilometers per hour the whole time, your direction is constantly changing. So we actually do consider that an acceleration as well. So uniform circular motion is a fancy term for this type of motion. When we're moving at a constant speed, like the magnitude of the speed or the velocity is constant, but the direction is constantly changing in the path of a circle. So 25, these would all be 25 kilometers per hour, and that is an example of uniform circular motion. So driving a car in a circle at a constant speed. This type of acceleration has a special name. It's called centripetal acceleration, which you'll see right down on the page below. And the definition here, the equation for it, is actually if you start with this definition of acceleration and you do a little bit of algebra having to do with a constantly changing direction in the path of a circle, you end up with this expression for centripetal acceleration. So again, that's just the acceleration of an object traveling in a circular path. So for example, let's do example 1. A car is traveling down the highway at 100 kilometers per hour. It goes around a circular bend with a 600 meter radius. So here's our 600 meter bend. Right, we'll assume this is down the center of the road. We'll assume the radius looks something like that. That's the radius of curvature is 600 meters. And here's our car. And at that point, it's traveling at 100 kilometers per hour. So when we use our equation for centripetal acceleration, you notice we're going to be dividing our velocity squared or our speed squared divided by the radius. So we should make sure the units are correct. And our radius is going to be in meters, so our speed should probably be in meters per second, not kilometers per hour. So just sort of off to the side, I'll do that conversion. If we start off with 100 kilometers per hour, we convert the kilometers to meters, so that's 1,000 meters per kilometer times 1 hour is 3,600 seconds. So 1 hour is 3,600 seconds. Those units will cancel out, the hours, the kilometers, and it's the same thing as basically just dividing by 3.6, right? Again, that's the quick conversion between kilometers per hour, meters per second, divide by 3.6. And I believe you get 27.77 repeating, so let's just do 4 significant figures here to make sure that we're okay, because I think the final answer is probably going to have 2 significant figures. So 27.78 meters per second is how fast we're traveling. Let's put that here as well. Okay, so now we have everything we need to plug into our equation. So let's do that. So the velocity, or the speed, is 27.78 meters per second, all squared, over 600 meters, right? And if we do that, 27.78 squared divided by 600 is 1.28, I'll round to 1.3, so for two significant figures. And this is going to be, well, let's look at the units for a second. If we're dividing meters per second squared, so that's all squared, so it's like meters squared per second squared, and then we're canceling out one of those meters down here. So it's like let's just do this on the side. It's like you're doing meters squared per second squared, and then you're dividing it by meters. So what's going to happen is that one of those is going to cancel out, and you're left with meters per second squared, which makes sense. That's what we usually use as our unit for acceleration, right? Now, the second part of the question is, what direction is the acceleration in? And this is a little bit counterintuitive, probably. You might think the direction of the acceleration is in the direction that the car is traveling. But if you think about it, in the direction the car is traveling, it's actually not changing its speed, right? It's always moving at 27.78 meters per second, no matter what direction that car is traveling. The direction is constantly changing. So in actuality, the direction of the acceleration is in the opposite direction, not the opposite direction, but it's not in the direction of the motion at all. It's the perpendicular direction to the direction of the motion. So the acceleration is actually towards the center of the circle. So this is the centripetal acceleration, and that's always true for centripetal acceleration. The direction of acceleration is always towards the center of the circle. And again, it's because the speed is not changing in the direction of the motion. It's changing. It's sort of like it wants to go in this direction, but the acceleration is pulling it towards the center of the circle to make it follow this circular path. That also might make more sense when we start talking about the forces involved here, which we'll get to in the next little bit. So anyways, that is the answer. 1.3 meters per second squared, and the direction is towards the center of the circle. So that's going to be a constantly changing direction, right? Because as you move around the circle, you're pointing towards the center of the circle. So for this case, if you show it with an arrow towards the center of the circle, that is fine for this case. Now, there are some other equations for centripetal acceleration, and that's in terms of period and frequency, because something that follows the path of a circle could potentially be like repetitive motion, right? You can keep going around in the same circle and over and over and over again. And when we're talking especially about things that are moving fast, like a computer fan or like fans or things like that are moving around really quickly, we usually talk about them in revolutions per minute, RPM, or hertz, right? Which is a measure of frequency. Or period. Period's the other one that we usually do, and period just refers to the length of one rotation, right? So if you do a little bit of algebra, you start with this equation up here, do a little bit of algebra with the circumference of a circle, basically, you end up with these two equations. So again, here, T in this equation is period. And if you're a little bit rusty on that, again, it's the time of one cycle. Right, so it might be, it'll be seconds in this equation. If we want the units to come out nicely, we should use seconds. And in the other equation, we have this f, and r is obviously the same. It's still the radius of the circle, but f in this case is frequency. And frequency, it's usually measured in hertz, which is cycles per second. Right, that's the most common. The common measure of frequency. All right, so let's do a question with these equations. So a computer fan spins at 150 RPM. If the diameter is 12 centimeters, determine the centripetal acceleration of the tip of one of the fan blades. So picture, a fan here. I'm going to draw a horrible fan. There's a fan. Let's just pretend that's a nice fan. It looks sort of like a flower. It says the diameter is 12 centimeters, which is 0.12 meters, right? And it's looking for the acceleration of the tip of one of the blades. Notice how, depending on where you are, like, it's going to be a different centripetal acceleration because it's based on the radius, right? So I have to specify that I want you to find the acceleration of the tip, because that's going to be different than the acceleration of like halfway down the blade of the fan, right? Because there's a different radius. But anyways, the radius is going to be half of that diameter, right? So we'll assume it's 0.06 meters, right? That'll be the radius of that fan. And we're given 150 RPM. And RPM is revolutions per minute. So that's how many times it spins per minute. That's actually a very slow fan if it only spins 150 times per minute. So that's not very fast. That's a very slow fan. But the unit we usually like to use for frequency is hertz. So we need to turn it from revolutions per minute to hertz, cycles per second. So 150 is cycles, like a revolution is just a cycle, right? Cycles per minute, right? So we should convert that to cycles per second. So all we need to do is multiply by 1 minute over 60 seconds. So basically just divide by 60, right? So 150 divided by 60 gives us 2.5. So this is 2.5 hertz, right? Because a cycle per second, the minutes cancel out, and then a cycle per second is a hertz. So 2.5 hertz. That is an extremely slow fan. I should have done some higher numbers there. Fans usually, they can get up to hundreds of cycles per second, a really fast fan. So that's our frequency, that's our radius, and that's all we need for the equation, right, for the centripetal acceleration. So our centripetal acceleration is 4 pi squared radius times frequency squared, because we have the frequency, not the period. And if we plug in numbers there, we will have 4 times pi squared times 0.06 times frequency squared. That gives us an acceleration of 14 we'll do 2 significant figures. So round that to 15 meters per second squared. Okay? And again, notice I don't put the arrow on top of the acceleration here for centripetal acceleration because the direction of the acceleration is constantly changing. We usually are just looking at it in terms of the magnitude and not the direction, because we know the direction is always towards the center of the circle. So there's our answer. And here's example 3. Always with any of these questions, pause the video, try it yourself, and then I'll do the solution if you get stuck, or you can check your answer. All right, a child on a merry-go-round, so same idea, but you have, a person sitting on a merry-go-round, and they're going around the circle, and it's telling us what the acceleration is, the centripetal acceleration. And if they sit 8 meters away, so the distance from the center, basically, the axle, the center of rotation, is 8 meters. That's the radius. What is the period of the ride? And remember, the period just means how long it takes to go around one cycle. So because we're dealing with period here, we should probably look at this equation, and we realize we have the radius, we have the acceleration, we should just be able to solve for t, right? So acceleration is 4 pi squared r over t squared. And if I rearrange that for t, I should get that t is equal to the square root of, what's it going to be? 4 pi squared r over a. Centripetal acceleration. There we go. So we should just be able to plug everything in here. And if we do that, 4 times pi squared times 8 divided by 0.85, and then take the square root of that, we should get 19.266, or to two significant figures, 19 seconds. Okay, and that's the period. So that's how long it takes to the merry-go-round to go around once. There we go. There's our introduction to centripetal acceleration and uniform circular motion.